Okay, hi everybody. So let's do number 1. Carefully explain, using words, pictures, and formulas, the definition of the derivative of a function of several variables, f of x, y, and how we must change the definition from single variable calculus. Okay, so here's my answer, although I'm noticing now there are no pictures. There are words and formulas, so I'll try to think about how to add a picture, but let's begin. It begins in blue. A function f of capital X of many variables is differentiable if an error function g of h exists, with the limit being 0 for small movements h, and the linear approximation formula blah 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 holds, is a true formula for any vector capital H. Note that grad f of x appears in the formula, which means all the partial derivatives must exist for this to make any sense. So really, the definition of the derivative is basically to make this formula true. If this formula can be true for some error function that goes to 0, we don't care much about what that error function looks like as long as it goes to 0. So that basically the difference between these two values is a very simple dot product with a gradient vector. Okay, so that's the definition of the derivative, which I guess if we had to say one of these things is the derivative, it'd be this thing, the gradient. But really, it's not about calling something the derivative. It's really about this formula. Why can't we just use the old definition from single variable calculus? And why am I doing this in pink? Why am I doing it? That part in pink, why am I doing it? I don't know why I chose the color pink, but how we must change the definition from single variable calculus. So I have to talk about that. I have to talk about the definition from single variable calculus. So here I go. Why can't we just use the old definition from single variable calculus? Here's the old definition. It looked great, but just do it with vectors. Well, because you can't divide by a vector. That is why. Now, in green, I have sort of some things. If we're going to call this the derivative, then it better match the thing in single variable calculus. Like, we should be able to use this in single variable calculus too. Otherwise, why are we even calling this the derivative? So here I go in green. Okay, but does this new definition match the old one? In other words, could we have defined the single variable calculus derivative like this too? The answer is yes. First, and then second. First, if we assumed that some error function exists with the limit being 0, and that this formula is true in single variables, then can we recover our old single variable definition for this thing? Well, yeah, subtract f of x, so we get this numerator, divide by h, so that we get this thing, and then let h go to 0. And that's our old definition on the left-hand side. And the right-hand side, the h's cancel. This is either a +1 or a -1, so it's totally irrelevant because g of h goes to 0 as h goes to 0. Okay, so we could have used this definition in single variable calculus. The derivative is the thing that goes here to make this equation, this linear approximation formula, true. And that's what the derivative is. Okay, well, that's great. So if we assume this new definition, we can recover the old one. How about we assume the old and recover the new? If we start with the old definition like this, then we can define the error function to be how badly they are different. And note there's no limit right here. There's a limit secretly hidden inside of there. But the point is that for any actual non-zero h, this is slightly different than the derivative. This is an approximation to the derivative. And so the difference is the error. That's our error. And yeah, this doesn't make sense when h is 0 because you can't divide by 0. So define g of 0 equals 0. Well, if we just take this formula, add f prime of x to both sides so that this moves over there, multiply by h, and we get exactly the new linear approximation formula. So you can do that algebra, it's not difficult. And that's perfect, aside from an annoying absolute value sign that is not there, which we won't worry about too much. If you really want to worry about it, then you can define this to be phi of h, and then define g of h to be phi of h if h is positive, and define g of h to be minus phi of h if h is negative, and then define g of 0 equals 0. And then you have, if you work it out, you have taken care of this annoying absolute value sign, but we won't worry too much about that. That's it. That's all I have. There's really, I mean, okay, how do I add a picture to this? This linear approximation formula. If here are my space of x1, x2, x3, whatever, and I'm at some point capital X, and I move some vector capital H, then that's sort of what so capital H is a movement, and I can basically recover the difference here by just doing the dot product of the gradient with this movement. And so that's maybe a picture that's nice there. Of course, a picture for the single variable calculus, we like graphs of functions, and so maybe this is x plus h, this was f of x, was this height, this was f of x plus h, was that height up there. And so we have the rise divided by the run, which is h, and the rise is the numerator. So there's a picture. And this is all just sort of formulas and words. I don't really know how to make this into a picture, because most of it was just silly little algebra to sort of massage one formula into the other formula, and then massage the other formula into the one formula. So there's, algebra doesn't really get pictures very, very easily. Okay, that would be my answer for number 1.